Good morning, everyone. Today we will see subset sum problem using backtracking approach. First, we will see what is subset sum problem. Given a set of n positive integers, set is given with n positive integers and sum d is given. Okay, the problem is to find the subset of integers whose sum should be equal to the given target d. D is also integer. So the problem set of values are given and sum is given. We have to find the subset from the given set and the sum of values of element in the given set should be equal to the sum D. That is, find a subset of integers whose sum should be equal to given integer D. And it is a very classical problem in computer science field. It can be solved using dynamic programming and backtracking approach. Here, integers are given, sum is given. Find the subset of the given set with sum equal to the given target. See the example. First example, there are 4 values, n equal to 4. Number of elements in the set is 4. And the target sum is given 9. We have to find the subset from the given set. And the sum of elements in the subset should be equal to the target D. And see the example, 3 plus 4, 7 is not equal to sum. Again, 4 plus 5. If we add 4 and 5, that is 4 and 5 is a subset of given set. And the sum is 5 plus 4 is 9. And for this type of problem, we have more than one answer or no solution. Problem can have 0 solution or 1 or more than one solution. And second subset is, if we take 4 plus 3 plus 2, that is 4 plus 3 plus 2 is 9. So we have another subset whose sum is equal to 9. And see the second example, there are 6 values. Sum target is 9. The subset is only one subset, 4 plus 5. Sum is equal to 9 and there is only one combination. And third example, there are 4 elements. Target sum is 8. There is no solution. If we take any combination of the numbers and the sum is not equal to the given target D. So these problems have no solution. So these type of problems have no solution or one or more than one solution. And what is backtracking? Is a problem solving strategy. It can be applied where there are many possibilities to find the solutions. So that we can try in multiple ways to find a solution. So in that case, we can apply backtracking. If we are moving in one direction, solution path, if the current state does not lead to a solution or optimal solution, we can stop at the state. We can move back to the previous step to find the other option, that is called backtracking. If one option does not give the optimal solution or valid solution, move back to the previous step and explore the remaining possibilities. Here, there are more possibilities to find this problem. So in this case, we have to try all the possibilities. Even though we got answer or solution for the given problem in the first path, we have to try all the possibilities to find another answer. So the current possibility lead to a solution is called solution end. If we are moving on path, if the path leads to a solution, that is called solution end. If one path does not lead to a solution, is called dead end. So there are two results in backtracking approach, solution end and dead end. Solution end means the path gives a solution. Dead end means the path or the current state does not lead to a solution. That's called dead end. And what are the steps in backtracking? Form a state space tree to represent solution space. And we are representing the solution space in the form of state space tree. The tree has root node. It is a hierarchical structure. It has a parent-child relationship. Root node is always initial solution. Then that can be explored in multiple possibilities in the next level. Again, the next level, second level, the current states are explored for my next level. So every level, the node is explored if there's a possibility to give a solution. At some point, there is no possibility for finding optimal solution. We can stop the process, and that is called dead end. We can move back to the previous step to find other options. The current path does not lead to a optimal or valid, it is called dead end. Stop the process, move back to the previous step, find another possibilities. This process is repeated until all the possibilities are explored. Here, this problem can be applied where there are more possibilities to find a solution. So, you have to try all the possibility solution path to find the result. Finally, return the state space tree with zero solution or one solution or more than one solution. That is the basic concept of backtracking. And see the example, state space tree. Tree contains root node, that's the initial solution. That can be explored to the next level. Then every level, the current node is explored. And see the example, some D is given 15. There are four elements, 3, 5, 6, 7. So we will see how to draw a state space tree. So tree node, root node is always 0. In the case of subset sum, so we are going to find the sum value. Or if we are finding sum value, initially we are assigning as 0. So this is the same concept. Root node value is 0. And there are four elements. For the first level, take the first element. First element from the given set 3. 3 is taken for first level. So in this level, there are two edges, left edge and right edge. Left edge is with adding the number. Right edge is without adding the number. So the take 3, 3 is added with the root value 0. So if you're adding 3 with 0, the left root value is 3 and without adding 3. So we are not going to add 3 the right side. So the root value remains 0. That is level 1. Level 1, we are taking the first element. Next, we are going to expand to the level 2. For the level 2, there are two nodes, 3 and 0. So we are going to explain 3 and 0 for the next level by taking the second element from the given set. So what is the second element in the given set? 5. 5 is the second element. So now we are going to explore these two nodes with element 5. So take the node 3, left edges with adding 5, right edges without adding 5. And for 0, left edges with adding 5, without adding 5. So for 3, with adding 5. So if you are adding 5 with the 3, the sum is 8. Right side without adding 5, the root value 3 remains as it is. And the right side 0, if you are adding 5 with the 0, the next child value is 5. If you are not adding 0, 5, the 0 value same as the root value. And the second level is over with the second element 5. Next we are going to third level. Third level, take the third element, that is 6. 6 is the third element. Now every left edges with adding 3, there are 4 nodes in the next level. First level only one element node, second level 2 element, next level 2 power 2, 4 elements are there. So every state with the power of 2. And next level, there are 4 elements. For all 4 elements, left edges with adding 6, right edges without adding 6. So the root 8, if you're adding 6 with the 8, the value is 14. So now see the target, our aim is to get 15. Now the value 14, which is less than, if you're adding 6 with 8, so value is 14. Next, right side, without adding 6. So right, I8 as it is. And then for an element 3, 3 with 6 is 9. And right side, 0 with 0 is, 0 with 3 is 3. And for the node 5, 5 plus 6 is 11. Next, without adding 5. So this is the concept. Now, we are going to the fourth level by taking fourth element 7. C7, we are at, there are uh, 8 elements in the third level. So all 8 elements, we are creating tree with left edge, right edge, with the adding 7, right edge is without adding 7. So first take the node 14. If you are adding 7, that is greater than 15, that is not feasible. Our aim should be equal to, the target should be equal to 15. So if you are adding 14 plus 7, which is greater than 15, so it is not feasible. It's called dead end. This path will not give solution, that is called dead end. And take 8. With the 7 is, if you are adding with the 7, that is 8 plus 7, 15. 15 is our target, D equal to 15. Now we got 15. Take the path. This one answer. Okay. Next, we will see other options. So 8 without adding 7, 8 which is less than 50. Now we can find out. There are 4 elements, 4 levels are over. So we can't explore further. So we can stop and we can conclude the result. And 9, take 9. If you're adding 7, 9 plus 7, 16, which is greater than target. It's not feasible. And 3. 3 plus 7, which is less than 15, which is not feasible. Should be equal to 15. And for 11, 11 plus 7 is 18, which is greater than 50, dead end, not solution. And 5 plus 7, 12, which is less than 15, it's not feasible. And 0 plus 30, which is less than 50, and this is not feasible. Now for this problem, we have only one end, one node, solution end, that is solution. 15 is solution. See, all the remaining nodes are dead end. The state space tree leaf node should be labeled with either solution or not feasible, dead end. Solution or not feasible means less than 15 or greater than 15, that is called not feasible. Now, how to write the solution? See the path from root to the solution. 0, 3, 8, 8, 15. So see all the path, see the edge, all in the solution path. So in the solution path, take the node only with the adding 3 and with the adding 5. Take 3 and 5 and see the path without adding 6. So we should not take the edge without adding. So without adding 6, we are getting the result. So should not add 6 in the solution set. So the only the path is 3, 5, 7. See the path from 0 to 15 with 3, with 5, without 6, with 7. So without edge should be removed and take only with 3, 5, 7. That is the final result. And what is state space tree? So we have hierarchical structure to represent how the problem is solved using backtracking. In root node is always initial solution that can be explored level by level. Each level we are taking the value from the given set. We are adding, there are two edges. We can generate a state space tree by giving two edges, left edge and right edge. Left edge is with adding this corresponding number in the level. Without adding is without adding the element in the corresponding level. And what is promising node? Non-promising node. A node which is which promise to lead a solution, which can give a solution to the given problem. This is called promising node. The node can lead to a optimal solution or feasible solution to the given problem. This is called promising node. Not promising node means the current node does not give a give a optimal solution, or that does not lead to a optimal solution or feasible solution. That is called non-promising node. So now promising means it will give lead to a success path. Non-promising means does not lead to a solution path. And state space tree is a conceptual tree used in backtracking to represent all possible combinations or states for the given problem. So there each node represents a partial solution. Take the root node, that is initial solution. Take the leaf node, that is a final solution or dead end. So nodes between root and leaf is called intermediate nodes, which shows the intermediate results of the problem. So there are two edges, left edge and right edge. Left edge is always adding number with the root value. Right edge is without adding the number. This is the basic concept of state space tree. There are three expansions, three operations in a state space tree. First one, expansion, explorations. So every level, the node is explored to next level. It's called expansion. What's the backtracking? Going back to the previous node if dead end is reached. If you're moving on path, it is not feasible to expand further, move back to the previous, find another option that is called backtracking. What is pruning? That is mainly used to increase time complexity, efficiency. Pruning is ignoring certain branches based on constraints. Or for optimization problems, we have some constraints. Based on the constraints, some branches can be eliminated or cannot be explored. So that's called pruning. Removing unwanted operations from the state space tree is called pruning. It is mainly used for generating optimal solution. And see the example. See the example. 3, 4, 5, 2. There are four values. Target is 9. And we will see how we can generate the solution. I told you we are going to draw a state space tree, and the root value is always 0. So left edge is with adding. W means with adding. WO means without adding the number. So there are four elements in the given set. 3, 4, 5, 2. There are four levels. For the first level, take the first element 3. So left edge is with adding 3, right edge is without adding 3. With adding 3 means 0 plus 3 is 3. Right side, we are not adding 3, so the root value assigned as the child value. This first level is over. So after the first level, there are two nodes for exploring to the next level, 3 and 0. Now, take the element 4. For the second level, take the element 4. Left is with adding 4, right is without adding 4. So, 4 plus 3 is 7. So, next right is without adding plus 3 as it is. And for the second node 0, with adding 4, 0 plus 4, 4. Right side without adding 4. Now the second level is over. Every time the root value should be compared with the given target. That node value, we are generating new node value that should be compared whether it is equal to target or not. If it is equal to target, we got the result. We can stop the process. If it is less than the target, if there are any elements to be added, we can proceed to the next level. And 7 plus 5. 7 plus 5 is 12. Now, for the third level, you're taking 5. Left edge is with adding 3. So, 7 plus 5 is 12. 12 is, which is greater than target 9. So, this is dead end. Next, take 7. We are adding, with adding 2. With adding 2, so we are getting 9. So, which is equal to target 9. Which is equal to target 9. So fourth level, we are taking the element 2, we are adding with the node value. If it is greater than target, give the dead end. If it is equal to target, there is a solution. See the label, see the nodes in the leaf, either dead end or leaf, dead end or the solution. Now we got 9 one solution, and again 7 less than 9, so dead end less than and 10 greater than 9 dead end it's not a feasible. Again see the leaf 8 less than 3 dead end, dead end, dead end. And see we have one more result 9 without adding 3, then with 4, with 5 we are getting 9. There are two solutions in the slide. There are two solutions. So now take the path from root to the current node I, solution node 9. Solution node 9. See the path. So see the first one, 0 to 3, 3 to 7, 7 to 7, and 7 to 9. In this path, take only the element with the adding. So first one is with adding 3. 3 can be taken as the result. See the result set 3 is added. Next with the adding 4. So 4 can be added. 3 comma 4. Then without 5 means we should not, without adding 5 we are getting this result. So we should not add 5 in the solution without 5 and with 2. So now 7 plus 2 is 9. With adding 2 we are getting 9. So the result is 3, 4, 2. So the result is 9. See another solution, the path 0, 0, 4, 9. So in this path, they take only the element with adding. So first, initially without adding 3, we should not take 3. Then with the adding 4, with the adding 5. So 4, comma 5. So when we see the solution path from root node to the solution node, see the path, take the element only with the adding. So without adding element can be eliminated in the solution set. So there are two solutions, 3, 4, 2 and 4, 5. This is the final subset problem solution. And what's the time complexity of subset sum problem? The subset sum problem using backtracking has an exponential time complexity. So T of n is order of 2 power n, because every iteration we are expanding 2 power n combinations, initially 0. So next to 1 power 1 is 2 element. So 2 power 0 is 1, 2 power 1 is 2. Next level we are having 2 elements. For the third level we have 2 power 2, 4 elements. Next level 2 power 3, 8 elements. So every iteration we are expanding with 2 power n nodes. 2 power n nodes. So the time complexity is order of 2 power n. At each step for each element in the set, the algorithm decides whether it's included or excluded. When whether we can include the element with the adding number or without adding, without including. This creates a binary decision tree with 2 power n possible subsets. And the algorithm explores all possible subsets to find one or more whose sums would be equal to the target. So worst case condition, all subsets are explored without pruning. There is no pruning happen in the worst case. All subsets are explored, especially bad when target sum D is not achievable. So we are getting only smaller number of values, but we have the more target that it cannot be achieved. So that in this case, the worst case, we are trying all the possibilities. For a set S, S1 equal to Sn, the state space tree depth is n, because n number of elements, so n number of levels, the depth is n. Each level two choices, two total nodes is 2 power n minus 1. So each node, each level, there are two choices, whether we can add or we cannot add. So there are two options. So every level makes two choices. So the time complexity will be 2 power n minus 1. Thank you.